Isn't it fascinating that invisible radio waves bring text messages, voice calls, and social media content straight to our phones? And have you ever tried to imagine how that data actually travels through the air? Since I have started working on my PhD, I often try to imagine that, and I invite you to do the same while I explain how wireless signal propagation can be made more efficient. Let's look at this simplified illustration. Imagine an antenna sending out multiple rays in different directions. Some of them go straight to your phone. Others take a detour. They bounce off every building along the way, following the laws of reflection. When your phone sees many useful reflections, the connection is strong. When reflections are few, the received signal becomes weak. And this is what we experience every day. In future wireless networks, it is expected that high-frequency signals are used which can carry large amounts of data. These signals, however, are more directive, more like focused beams, which means less reflections and more places where this high-speed connectivity will not be available. So how to fix that without installing additional expensive cell towers? One promising idea is to influence these reflections themselves, to steer radio waves where we want them to go. How's that possible? Imagine a wall covered with many tiny reflective elements, each controlled by software, which can shape the reflection of an incident wave. This is called a Reconfigurable Intelligent Surface, or RIS. The challenge is to correctly tune thousands of these elements, which can be, in practice, quite complex and difficult to achieve in real time. My research focuses on a pragmatic compromise. Instead of real-time optimization, I look at collections of pre-computed RIS configurations called codebooks. In this case, the configuration complexity reduces significantly. Well, it is still not straightforward to design these codebooks. They must, for example, match the considered communication scenario. They must balance between wide-angle and narrow-angle reflections, and they must match the size of the RIS and its reaction time. In my publications, I have analyzed these design trade-offs for typical communication scenarios. For example, I have derived an optimal RIS configuration that improves the reliable detection of active devices, which is a core task of every wireless communication network. Also, I have analyzed the trade-off between RIS, gain, and configuration complexity, and I have shown that very large RISs can be controlled with nearly zero overhead. And I have identified how a RIS can operate without any external power supply, just enabled by harvesting energy from the incident signal. Taken together, my research provides valuable guidelines for moving RIS technology towards reality. So next time the signal indicator on your phone shows one bar only, imagine how a RIS on a nearby wall could steer the radio signal directly your way. Thank you.